Module 8, Resource Management and Monitoring. Although the VM kernel works proactively to avoid resource contention, maximizing performance requires both analysis and ongoing monitoring. Lesson 1, Virtual CPU and Memory Concepts. By the end of this lesson, you should be able to discuss CPU and memory concepts in a virtualized environment, describe what overcommitment of a resource means, identify additional technologies that improve memory utilization, and describe how VMware vSphere virtual symmetric multiprocessing works and how hyperthreading is used by the VM kernel. When running a virtual machine, the VM kernel creates a contiguous addressable memory space for the virtual machine. This memory space has the same properties as the virtual machine address space represented to applications by the guest operating system. This space allows the VM kernel to run multiple virtual machines simultaneously while protecting the memory of each virtual machine from being accessed by others. From the view of the application running in the virtual machine, the VM kernel adds an extra level of address translation that maps the guest physical address to the host physical address. So what happens is on the ESXi host, as you can see, these addresses map through on this graph as right here. This will be your application running, and it gets its pages from memory from the operating system, but it's mapping it to the physical memory here. But as you can see, it's in different spaces as if it was running on the machine. And the same from this application. It gets its own space in the ESXi host, but the virtual machine's giving it a different address. It's taking an address here, and it would be the same with another virtual machine. It wouldn't be using the same memory spaces. Virtual machine memory overcommitment. Memory is overcommitted when the combined working memory footprint of all virtual machines exceeds that of the host memory sizes. Virtual machines do not always use their full allocated memory. An ESXi host transfers memory from idle virtual machines to virtual machines that need the memory to help improve memory utilization for that virtual machine that needs it. Memory overhead is stored in a swap file. Just like with Windows or Linux. Linux, you have a swap partition. Windows, you have a swap file. When you run out of memory, the machine starts swapping memory pages to a file on the hard drive. It starts using a hard drive, which is why your machine will get slower, because your memory transfers quicker than your hard drive. For example, let's say you have a host that has 4 gig of RAM, and you have 4 machines, virtual machines set up with 1 gigabyte each of memory. If all virtual machines are idle, then let's say the combined consumed memory might be below 2 gigs. But if all 4 start using the memory and the footprint will exceed 4 gigabyte between all of them, you've just had overcommitment. It will start swapping out to the swap file, just like your normal computer would. But as you see, this is taking place on the level of, this is its virtual hardware. It's swapping out that memory to a disk. So it's going to slow all multiple virtual machines down, possibly, if all of them start swapping. Memory reclamation techniques. The VM kernel will use various techniques when reclaiming memory on an ESXi host. The first technique economizes the use of physical memory pages and is known as transparent page sharing, or TPS. TPS allows pages with identical context to be stored only once. Workloads that consist of multiple virtual machines often consume less memory than when they would running on physical machines. But this is because of TPS. In essence, take Windows for example. Every Windows installation has an explorer.exe, and it uses memory. So you have 2 virtual machines with Windows. That Explorer exe, let's say it's using 100 meg of RAM. The second host will not be running that much because the EXEs of Explorer.exe, the footprint of the memory is the same. So therefore, it will not have to double the memory. It's kind of a way of deduplication, not really deduplication because it's not really deduping it, it's just sharing it. During times of memory contention, the VM kernel looks for opportunities to reclaim idle or allocated but unused memory from virtual machines. So if you have a machine, you've allocated 4 gig to it and it's only using 2 gig, there's 2 gig that the VM kernel can reclaim. The VM kernel transfers this memory from the idle virtual machines to machines that need more memory using the Vsicm6 driver, or if you want to call it VM mem control driver, that is typically installed with the VMware tools. Now, the machine that it needs to reclaim the memory from will need to have VMware tools installed. This is also what's known as the VMware memory balloon driver, or they can call this ballooning. Another technique is memory compression, and this reclaims more memory by compressing pages when the contention's high to avoid swapping to a virtual machine. Another option for reclaiming memory space is to create a host cache on a solid state drive on the host machine on your ESXi host. This host cache will be used for TPS, ballooning, and memory compression. So what it'll do, it'll help it's kind of swapping it out. Well, it is swapping it out, but it's doing it to a solid state disk store, which is a lot faster than mechanical drives. Virtual SMP, or symmetric multiprocessing. You can configure a virtual machine to have up to 128 virtual CPUs, or vCPUs. The VM kernel includes a CPU scheduler that will dynamically schedule vCPUs on the physical CPUs of the host system. The VM kernel scheduler considers socket core thread topology when making scheduling decisions. AMD and Intel both have developed processors that combine multiple processor cores into a single integrated circuit called a socket. This socket is a single package that can have one or more physical CPUs, each core having one or more logical CPUs or threads. Logical CPUs, or LCPUs, provide the core with the ability to schedule one thread of execution. Each logical CPU provides the core with the ability to schedule one thread of execution. On the slide, the first system right here is a single core dual socket system that has 2 cores and so 2 logical CPUs. So here we give this virtual machine 1 CPU and he will schedule 1 logical CPU. This one has dual virtual CPUs, and you see it scheduling it on the hardware 1-to-1 correlation. This is on a dual. Now, as we can see here, we have 4, and it's scheduling each one to each logical CPU. When a vCPU or a single vCPU or multiple vCPU virtual machine must be scheduled, the VM kernel maps the vCPU to an available logical processor. Like this guy, we could go add another CPU and it will map to that logical CPU because he has a logical CPU available. Hyperthreading. If you have hyperthreading enabled on your system, on your ESXi host, the ESXi host can execute 2 threads at the same time on each processor core or physical CPU. Hyperthreading provides more scheduler throughput. So as was reading in the last slide, one CPU can be scheduled on one logical CPU. Well, now another one could be scheduled on it. As it's showing in this example, this guy has 2 CPUs, only one on one physical CPU, but he's got 2 logical CPUs available. So we can schedule those, any processing done that can be scheduled on that core because it has hyperthreading on there. The drawback of hyperthreading is it does not double the power of a core. So if both threads of execution need the same on-chip resources at the same time, one thread has to wait. So it gives it a little bit of latency. But still, the ESXi uses recent advances in hyperthreading technology, and on systems that use these new technologies, performance has improved. An ESXi host enabled for hyperthreading should behave almost exactly like a standard system. Logical processors on the same core have adjacent CPU numbers. So logical processors 0 and 1 are on the first core, logical processors 2 and 3 are on the second core, and so on. If you want to ensure hyperthreading is enabled, you can enable it in the BIOS of your system. And when you use the vSphere web client to ensure the hyperthreading for your host is turned on, you can access the hyperthreading option. You go to the host summary tab and select the CPUs under hardware. CPU load balancing. The CPU scheduler can use each logical processor independently to execute virtual machines, providing capabilities similar to traditional SMP systems. The VM kernel will intelligently manage processor time to guarantee that the load is spread smoothly across processor cores that is in the system. Every 2 to 40 milliseconds, depending on the socket core thread topology, the VM kernel looks to migrate vCPUs from one logical processor to another to keep the load balanced. The VM kernel does its best to schedule virtual machines with multiple vCPUs on 2 different cores rather than on 2 logical cores on the same core. But if necessary, the VM kernel can map 2 vCPUs from the same virtual machine to threads on the same core. If a logical processor has no work, it is put into a halted state. This action freezes its execution on resources and allows the virtual machine running on the other logical processor on the same core to use the full execution resources of the core. The VM kernel scheduler properly accounts for this halt time. So a virtual machine running with the full resources of a core is charged more than a virtual machine running on half a core. This approach to processor management ensures that the server does not violate the ESXi resource allocation rules. You should now be able to discuss CPU and memory concepts in a virtualized environment, describe what overcommitment of a resource means, identify additional technologies that improve memory utilization, and describe how vSphere Virtual SMP works and how hyperthreading is used by the VM kernel.